This chapter talks about several important items that we will need for regression analysis. The first one talks about weighted least squares, and I'm on overhead 3. The usual regression model assumption has been that the variation in the random errors and the variation, therefore, in the y response variable is a constant for all observations, standard deviation of sigma. And what we're going to do is talk about assumptions, and we're going to talk about what to do when this particular assumption has been violated. So here's a way that we can express the variance function of the response in a more general way. The variance function for a random error can be expressed as sigma squared divided by wi, where wi stands for a weight, and it gives a different weight for every observation, potentially. And if every observation wi has the same weight, then we are in a constant variance situation like we've been before, and we don't have a problem. However, the way we're writing this is we are letting different observations possibly have different wi values, which would mean that different observations have different variances. And in the way we're doing this, an observation with a larger weight is going to have a smaller variance. So we're going to get used to this way of representing the variance function. There's a lot of data that can be like this. A real common situation comes from biology. I'm always seeing biologists that will have a response variable that's based on an average of n sub I observations. They averaged 3 plants in a plot, and that average biomass is their response variable. But maybe in another plot they averaged 12 plants, not 3. And so the number of observations that each particular average is based on might be different. And what you're supposed to remember from an introductory course in statistics is that the variance of an average is sigma squared over n, or the standard deviation of an average is sigma over the square root of n. And so, in other words, a different y observation might have a different variance because it's been based on different numbers of observations. Sample averages that have a larger sample size base will have a smaller variance, and observations that are based on fewer measurements are going to have larger variance. And so we can incorporate this information through the wi weight control mechanism. And in this case, what we would do is set the actual variance, sigma squared over ni, equal to our model hypothetical construction variance of sigma squared over wi, which can be written for any observation. What is the wi in this case? Well, wi is just ni, and observations that are based on more measurements have greater weight. What if the variation in the response is a function of the predictor? This is also really common. What do we do if, when a predictor value gets bigger, the variation in the response gets bigger? Well, what if the variation in a y value is sigma squared times the value of the predictor? Well, if that's the actual variance function, let's set it equal to our construction variance function of sigma squared over wi, and solve for wi, and we observe that the correct weight to capture the variation is that the weight should be 1 over the value of the predictor, 1 over xi. So in other words, when a predictor xi would be a big value, the observation will have a lot of variation, and therefore will give a small weight. And so the way we're looking at this here is that more variation gets a smaller weight, less variation gets a bigger weight in doing things. What if the variation in a response value is a function of the mean function? Well, this is going to be handled later in the course, but we would just set the weight according to this to be 1 over the estimated value of the mean function. Well, let's try to use this back in our analysis. Here's our usual model formulation. Y vector of observations is related to the predictors through this kind of multiple regression model. But what if the errors have this different kind of structure so that they're different variance depending on the weights? Well, the variance matrix for these errors is just a number, sigma squared, times a matrix that will have, where W is going to have the little weights on the main diagonal from northwest to southeast, and it'll have zeros on the off diagonals. Well, if this is the way the variation works, you can modify least squares estimation to take into account that some observations should be used and weighted more heavily than others. And in the second bullet, you can see that what we're doing is we have a sum of squared residuals inside these parentheses. Inside the parentheses we have residuals, and then we square the residuals on the outside there. But notice that every residual is given a weight as part of the sum. And that will use some observations more than others with different weights in the estimation. And so we'll use data differently depending on its inherent weight. And this technique is called weighted least squares. So here are the matrix representation for the estimates for beta parameters if we use weighted least squares estimation, and we use some observations at a higher weight than others. If we use them differentially, it's called weighted least squares. If we use the observations all equal weights, that's called ordinary least squares. And in this overhead, we're going to go through what we know about this kind of method. The second bullet says that, well, on average, weighted least squares estimates are, in fact, the true beta values, just like ordinary least squares. Remember, for ordinary least squares, we always found that on average, the estimates tended to represent whatever the true data generating mechanism was. And the same is true of weighted least squares. On average, the expected value of our beta estimates are the true values. So on average, we do the right thing. The important thing here is in the third bullet. Weighted least squares that use the data differentially tend to have smaller standard errors than ordinary least squares. And that is a very powerful and very useful thing. This estimation method tends to produce smaller standard errors for coefficients than ordinary least squares does. And that advantage comes from using the data with different weights. Here's an example of some data that would make good use of weighted least squares. We have some apple trees, and we're averaging the number of stems over a number of trees. And so, it's different numbers of observations depending on the unit. And so we're going to use these data to illustrate the technique. So we're going to be modeling the average number of stem units as y bar, and we're going to try to build a relationship between the number of days for the growth. Presumably, as the trees grow more days, you'll have different numbers of stem units. And so this is the LM function, just like you've seen previously. We have a y variable. We have a predictor variable x called day. The data frame is long shoots. It's a built-in data frame in the ALR3 library, the ALR3 package. And we're going to specify the weights. Remember, these are all sample averages, and so we'll specify the weights using the variable n. and n was defined earlier. That tells us how many measurements each observation is based off. And so we'll use weights as n, and this will tell R to use weighted least squares estimation. And we get our usual output table of beta naught hat and beta 1 hat estimates, standard errors, and so forth. This is how you would incorporate weighted least squares. You'd need to make a variable that will contain the correct weights. That is the crucial thing with weighted least squares. Here's just a demonstration of the data. Here are the average number of STEM units plotted against the number of days. You can see there is a nice straight line pattern, and we use our weighted least squares estimates from our model. Our model was A1. We'll use our weighted least squares estimates to put in a summary line, an AB line on this graph. Looks very good. What if we want to do a prediction, like predict the average number at, say, day 35? Well, what we do is we use the predict command. We use our weighted least squares model. We specify a data frame that has an observation of day 35 in it, and we're going to say that this observation is based on 10 measurements. We'll use the prediction option to predict the average number of STEM units, and when we do that, we get an estimated value of 17.58 with these confidence bounds. And I think it's just important to know here that you need to specify the appropriate weight when you make the prediction. Now we're going to move on to another important topic called the general F-test. And this is going to be used whenever we want to compare a null hypothesis model to an alternative hypothesis model, comparing two models. And this is probably going to be most useful when we want to test the effect of maybe more than one predictor at a time. In the fourth bullet, we mentioned that every predictor that is in the null hypothesis model also has to appear in the alternative hypothesis model. So in other words, the null hypothesis model is a subset of the alternative hypothesis model. The alternative hypothesis model is typically bigger and has more terms. The null hypothesis model is smaller and has fewer terms. And what we're testing is the need for these extra terms and extra structure between the two models. If the residual sums of squares is really different between the two competing models, it's going to mean that the extra terms and the extra predictors in the alternative model are going to be needed. Final bullet mentions that F-tests, like we're going to talk about here, depend on a normality assumption of the random errors. However, it turns out that the F-test works really well and is robust to departure from this normality assumption. So in other words, the normality of the errors assumption is not terribly crucial to ensure that F-tests and T-tests and confidence intervals are quite reliable. However, if there are really serious concerns about the normality of the errors, you can use bootstrap methods, like we've talked about previously and is mentioned in the text. Now we're going to talk about this general F-test. So here's how we specify it. We have a null hypothesis model that explains why in terms of a series of predictors x1 to xq, and our alternative model expresses the mean function in terms of the variables x1 to xq plus some extra predictors up to xp. So p is more than q. Every predictor that's in the null hypothesis is in the alternative plus some extra ones. The test statistic that we use to examine whether we need the bigger model is the general F statistic. And it looks quite complicated, and I guess it is. The numerator is really how much difference is there in the residual sums of squares between the null and alternative model, divided by, in the denominator, an overall measure of variation from the big model, the residual sums of squares, from the alternative hypothesis model. So really this is like almost like a percentage change. How much different is the residual sums of squares between these two models? So in the numerator of the numerator, it's just the subtraction of the two models' residual sums of squares. Remember that residual sums of squares are the amount of unexplained response variation. The amount of response variation that's not explained by the model predictors. And so if these two residual sums of squares are quite different, it means the models are quite different, and therefore it means that these extra predictors in the alternative really make a difference. And so if this F statistic turns out to be quite big, it is evidence that the alternative hypothesis model really is needed. Notice that in the numerator, we divide by the difference in the degrees of freedom between the null hypothesis model and the alternative hypothesis model. And so if this basically turns out to be how different are the sizes of the models, how many additional terms do the models have. That's what this difference measures. And because both the numerator and the denominator are residual sums of squares divided by degrees of freedoms in some sense, this is really some kind of a mean square for the drop or the change divided by the mean square for residuals. So these are mean squares divided by mean squares, just like F statistics always are. Then we move on to the p-value, and we just find out what's the probability that we could get an appropriate F random variable to be bigger than what we've observed from this test statistic. A small p-value, like I mentioned, tells us that the additional predictors are needed. A big p-value means we don't have enough evidence to conclude that the extra terms are really helpful. Here's a data example from our fuel consumption study, Fuel 2001, that we've looked at previously. I am creating a null hypothesis model here in NHMOD that explains fuel consumption per person in terms of log highway miles and tax, and a bigger alternative hypothesis model that explains fuel consumption per person in terms of those variables, log mileage and tax, plus the additional variables, DLIC and income. And I performed the F test using the ANOVA command, specifying the two models separated by a comma in the same command. And we get this kind of output here. We get output that tells us about the null hypothesis model, model 1, gives us the residual sums of squares for it. And then for model 2, the bigger model, we get the residual sums of squares for that one. We get the difference between the residual sums of squares here in this column further to the right, and we get the difference between the two, and we get the F statistic, and we get the p-value computed for us. So using the output that we're getting here on overhead 17, we can construct the F test in the pieces here like this. We have the null hypothesis, we have the alternative hypothesis models, and then we plug into the formula for the test statistic. Remember that in the numerator, it's the residual sums of squares for the null hypothesis model, 302192. And that comes out in the previous page right here. Null hypothesis residual sums of squares, 302192. Also in that numerator of the F, we have to subtract off the alternative hypothesis residual sums of squares, 193700. And that's right here coming from the alternative hypothesis model, 193700. The difference between the two models' degrees of freedom is 48 minus 46 degrees of freedom for a difference of 2. That's where we get this difference degrees of freedom here. The subtraction between these two residual sums of squares is the 108492. And that is going to form the numerator of the numerator. The denominator comes from the residual sum of squares from the alternative hypothesis model, and we divide by 46 the degrees of freedom for the alternative hypothesis model. And we get a final F statistic of 12.88, and you saw that before back here on the ANOVA command. And the output p-value, very small, very small p-value. And we make our conclusion. P-value means the data we've observed is really unlikely to ever happen under the null hypothesis conditions. It means that we've got evidence to doubt the null hypothesis, support the alternative, that the additional variables of DLIC and income are really helpful in explaining fuel consumption, even after we've adjusted for log mileage and tax. And there we get the right interpretation for this F-test. We can build an analog to an F-test testing the need for additional variables with something that's called a multidimensional confidence interval, or a confidence region. So you know a confidence interval is meant to tell you about reasonable values for a single beta parameter, but what if you wanted to study a range of reasonable values for a set of two parameters, like beta 1 and beta 2, or hypothetically a p-dimensional set of parameters? You can make a region in space that is likely to contain the true values of the data generating system. This is a very complex formula for the values that are reasonable for the beta parameters, but basically it forms an ellipse or some sort of region that is a simultaneous region for good, reasonable values for the parameters. So in this particular data set, we have some United Nations data set about countries that uses a response value of the log of fertility for the women in these countries, and we're going to explain it with per person GDP logged and the percentage of the population that is urban. And we're going to study the simultaneous confidence region of beta 1 and beta 2. So here is the percentage urban coefficient, beta 2. Here is the log of per person GDP, the beta 1 coefficient. And these regions describe simultaneous values of the beta coefficients that are reasonable for the original data generating mechanism. And we create these confidence regions using the confidence ellipse function from the CAR package, the CIR package. The innermost confidence ellipse represents an 85% simultaneous confidence region. The outer one is a 95% simultaneous confidence region. And I think the important thing to notice about this confidence region is that 0, 0 is not a reasonable thing to say about this set of coefficients. Here is 0 for the percentage urban coefficient, but the other coefficient value of 0 is off the chart and is like over here somewhere. And so it is very clear evidence from this set of ellipses that there is definitely some joint effect of the per person GDP and the percentage urban, and that 0 and 0 are not reasonable simultaneous values for these beta coefficients. What does seem to be reasonable for them is that both of them seem to be negative. If you look at the values that are in these confidence regions, the reasonable statements about those two parameters tend to be negative values. That's what we see from this set of curves. And if you look at the estimates, you'll see they're both negative, and you're supposed to notice that the center of this confidence ellipse is exactly at the values negative 0.18 and negative 0.0051. That makes the center, and we move away from the data beta hat estimates to form the confidence regions. You'll notice that the tilt of the confidence region was a negative tilt, and that means that those estimates are negatively correlated with each other. When one goes up, the other one tends to go down, and so forth. And the fourth bullet here, I'm mentioning the fact that 0, 0 does not seem to be a reasonable thing to say about the true underlying beta parameters for the GDP and the percentage urban. If you were to do an F-test for the need of these two additional variables in the model, you would find a small p-value for that F-test, signifying evidence that these two predictors are needed beyond just an intercept. The F-test will give a similar kind of conclusion to what the simultaneous confidence region view tells us, that 0, 0 is not a reasonable thing to say about these parameters. In other words, the two predictors really are going to be needed. And I hope that is helpful. Please let us know if you have questions about this material.